will decide this language. We'll call it N, right? Now we could, one approach is we could design this Turing machine N so that it operates in the same way as M, the previous one. In other words, that this machine N would simulate this machine B, where B is now an NFA. That's one approach. But there's another approach, and we will take this second approach because it introduces a new idea, which is useful for later. So we'll talk about this second way of proving things. And basically, the basic idea is that machine N will use M as a subroutine. So, in a sense, M is kind of incorporated as a part of N. So N is like a bigger machine that's using a smaller Turing machine, M, as a component, right, as a subroutine. Yeah, that's what I'm just saying here. So we'll have N use M as a subroutine. But there's a problem, and that is that M, the previous session, that machine accepts as inputs a machine B that is a DFA, not an NFA, a DFA. So what we first have to do, we'll go back to theorem in the first chapter, theorem 1.39. It was on page 55 of your textbook. So go back and refresh if you've forgotten. And that theorem says that it's possible you can convert any NFA into an equivalent DFA, right? Go here to refresh yourselves on how to do that. Okay, so that'll be our first step. We're going to, as part of N, the first thing it'll do is, besides checking the format of the angular bracket B comma W, besides doing all that, it will convert the NFA into the equivalent DFA, and then it will pass on the DFA, the converted, the DFA and the string W to its component M, and then M will do its job deciding whether that machine, B, C. Now it's C. Okay, sorry. Okay. Now after the conversion, once you've converted your machine, your NFA, call it B, and you convert that now into its equivalent deterministic finite automaton, DFA, call that equivalent machine, call it C. Okay, and then you pass on, in this form, you pass on C comma W, it's the same string, but this is now a different machine. Well, it's equivalent, does the same job, but this is now a DFA, whereas here this was an NFA. Okay, but you can convert this into this, and they're equivalent. Okay, so now use machine M as a component, as a subroutine, if you like, to process this string here, to see whether this string here, W, is accepted by this machine. Right? Now, if M accepts this, well then N accepts. And if M, the smaller component, so if M rejects this, well then N will reject. Okay, that's the idea. So in other words, if you're going to run the smaller Turing machine M
a vast virus database
in stage 2, so here's your description of the algorithm as usual in standard format, right? Open quotes, final quotes, the whole description's between quotes. The first line usually description of the input tape, right? Well, that's your input tape. Okay, and then the various stages. So the first step was to convert your NFA B into a DFA called C. Okay, and you use the technique to do that. Go and refresh yourselves from Theorem 1.9 on page 55. Okay, and then so here's your convert. This is now C is the DFA conversion of your NFA B, and you pass the DFA and the string to M, which is now a component of M, small part of N. Okay, and if M accepts, accept, and else, in other words, if M rejects, well then N rejects. And that's the description of the algorithm, right? So N will incorporate, contain in a sense, M, right? So you're looking on M as a kind of subroutine. Now, a bit of a comment just to fill in the last little bit. The next board we'll discuss 3 more decidable languages. There's this language, REX, regular expressions. So we're going to have a language of regular expressions. It'll be somewhat similar to what we're doing here. This is the empty language. Is a particular language empty? And EQ stands for equal. This is if your language would consist of an ordered pair of, so in angular brackets, your representation of 2 different automata, A and B, and the computational question is, are these 2 automata equivalent? In other words, do they recognize the same language? Okay, and we'll try to prove that the language, this language, we need to define what the language is, what the elements are, all those details. But we'll talk about these 3. We'll do theorems for each of these 3 on the next board, proving that they too are decidable. Okay, and there are also examples of how to convert computational problem into its equivalent membership of a language problem. Right? I'll stop there. 22 minutes.